All right, welcome back. This is the continuation of the first video, just to make it a little bit shorter. So in the last video, we talked about how velocity of an object moving in a circle will always move tangent, and the acceleration of an object moving in a circle is always going to be directed towards the center of the circle. Now, it's been a while since we have done forces, since we spent a lot of time and energy, so we need to remind ourselves of some things. So from last semester or first semester, we learned that objects that have changing velocities are accelerating. And changing velocity can mean speeding up and slowing down, or it could mean changing direction. Now, if objects are accelerating, they must have a force net acting on them. A force net means an unbalance of force. So not in equilibrium, but there is some force that is making the object be out of equilibrium. And finally, force net and acceleration are directly proportional, so it means they will always point in the same direction according to Newton's second law, which is force net equals mass times acceleration. Now, how does this look for circles? Well, we learned in the last video that objects moving in a circle are accelerating because they're changing their direction. Acceleration, we learned also, points towards the center of the circle, and therefore, being consistent with physics, the force net for circles must also point towards the center because force net and acceleration always point in the same direction. Now, we give force net for a circle a special name, and that special name is called the centripetal force. Now, I don't want you to get freaked out by centripetal force because really all it is it's the force net for circles. It's just given a special name. This is also known as the center-seeking force, okay? Because it is the force that is keeping things seeking, if you will, towards the center of a circle. So this is obvious. So in other words, this is the force that is responsible for keeping an object in a circle. Now, what I really need you to understand from this slide is that the centripetal force is not a force in and of itself. Rather, it's a combination of forces. So to understand this, let's look at a linear example. Let's say I was pushing a red box across a surface, and as I'm pushing it across the surface, I'm applying a constant force of 30 newtons to the right. Now, as I do that, the box is also experiencing a force friction of 10 newtons that is opposing the motion to the left. And so, what would be my force net acting on the block? Well, it would be force applied plus force friction, which, if I'm making right the positive direction, that would be 30 newtons plus the negative 10 newtons, oops, and that would come out to be 20 newtons. So my force net is equal to 20 newtons. But notice, there isn't a force net vector on the block anywhere, is there? No, force net was really just a combination of the actual forces that are there, meaning force applied and force friction. So in a circle, centripetal force is the same thing. It's not an actual force, it's a sum of the forces. And so let's look at a circular example. Now, the image might not be very clear, but when you're looking at this circular image, what I want you to imagine is taking something like maybe a yo-yo or keys on a lanyard maybe, and you're swirling it around in a vertical circle. Okay, so that's what that image shows you. And the reason why I have a blue and a red is to take a snapshot of the keys or of the yo-yo at two separate spots. So one is a snapshot of the yo-yo at the very top of the circle, and then the red one would be a snapshot of the yo-yo at the very bottom of the circle. Okay, so in the same way, let's go ahead and look at our centripetal force. So if I look at the first one, if I were to draw my force diagram of the yo-yo at the very top, I have the force gravity pulling down, because force gravity always pulls down towards the center of the circle, and I have force tension also pulling down towards the center of the circle. And that's it. That's all that's touching the yo-yo. At this point, it's a good reminder to remind you how you figure out what forces are there. So remember, back from the first semester, we talked about, first of all, ask yourself, what field forces are there? Meaning, what forces are there from some sort of field, being a gravitational field, an electrical field, or a magnetic field? Well, since gravity is the only one we've talked about up to this point, the only force that would be there would be gravity. And then the next thing you want to do is, after you've identified the field forces, ask yourself, what are the contact forces? In other words, what is actually touching the yo-yo. And the only thing touching the yo-yo is the rope. That is it. And so what force does a rope apply? And that's force tension. And so that's it. Those are the only forces that are there. And so force gravity and force tension are both facing directly down towards the center of the circle. Since they're both facing the same direction, we're just going to add them together. So force centripetal is just going to be a combination of my force gravity plus my force tension. And since they're both facing the same direction, they both have the same sign. And therefore, my force centripetal at the top of the loop would be 20 newtons. Now let's take a look at the bottom of the loop. First things first is let's draw a force diagram. Once again, I have gravity that's going to point straight down, and I have force tension that's going to face straight up. Now this time, the tension and the gravity are not facing the same direction, but instead they are facing opposite, meaning their values are going to take away from each other. By convention, and I will remind you this several times throughout the video series, for the circular motion unit, we are always going to make the force or forces that face the center of the circle positive. And so when you look at the bottom of the circle here, which force is facing the center of the circle, tension or gravity? Well, tension is the one facing the center. And so when I write my sum of the forces equation, it's going to be force tension and then plus negative force gravity. Or you can just write out force tension minus force gravity. Either way is fine, but just understand that the force that's not facing the center, in this case gravity, is negative. So when I find out what's my centripetal force, I'm going to take my tension force, which apparently at the bottom is 30 newtons, and I'm going to subtract the force of gravity, which is 10 newtons. And so that gets me a force centripetal of 20 newtons as well. Now you may be noticing, wait, the force centripetal is the same at the bottom as it was at the top. And that shouldn't come as a surprise because our centripetal force is going to be supplying our acceleration. And our acceleration should be constant because it's going in uniform circular motion. So it's not speeding up or slowing down, but it's just changing its direction. And so your centripetal force, as long as the speed is constant, your centripetal force will always be the same in a circle. All right, we will do lots of examples of this, but that's just a little introduction to centripetal force. Now at this point, it's a good idea to talk about the bad F word. Of course, there's many bad F words, and you should probably avoid all of them, but there's one particular that we're talking about here. We just learned on the last slide that there is a force called the centripetal force. This is the force that keeps objects in a circle. And I made a note here to saying this is a real thing. This actually is a real force. It does exist physically. But there's another force that a lot of people like to talk about and refer to as if it was real, and that is something called the centrifugal force, or centrifugal force, as some people call it. And this is defined as the force that pushes you out of a circle. But it's important to note that this is fake. There is no such thing as a centrifugal force. Now you might be wondering, well, why do people say it then? It's an easy idea. There's a lot of things in science at the introductory level that we refer to because it helps explain things, but then later on it causes a lot of confusion because you realize it wasn't quite true. And so let's contrast them right now. So what I want you to do is I want you to imagine that you were on a merry-go-round at a playground. I'm hoping you're not too young to remember that. Hopefully you remember back in the good old days when safety wasn't necessarily the #1 thing at playgrounds apparently. And they had these little spinning discs that you could stand on and they would spin, and they were merry-go-rounds. And they were really fun, very dangerous, but nevertheless very fun. And what would happen is you would spin so fast that you would fly off. Well, I want you to take a look at the first picture. Notice that you have all your buddies and all your friends standing on it, and you're spinning really fast in a circle, and you're all holding on to each other, and the person in the center is holding on to the center of the merry-go-round. This force that is keeping you in the circle, this is a real force, okay? This is a real force because you are actually holding on to each other. There is actually a force applied because you're being pulled in by your friends. So that's a centripetal force. It's the force keeping you in. But let's say your friend, who really isn't a friend at all, lets go of you, okay? You would feel pushed or thrown out of the circle. And so people would say, oh, it's the centrifugal force that's pushing you out. You are being pushed out by this centrifugal force. But that's fake. There's no such thing as a centrifugal force. There's no force that is pushing you out of the circle. So what's really going on then? If it's not a centrifugal force, what is it? It all comes down to Newton's first law, which, if you remember, Newton's first law was all about inertia. And inertia is an object's resistance to change in motion. So in other words, objects want to keep doing what they're already doing. Remember, we talked about in the last video that objects that are moving in a circle are moving in such a way where their velocity is tangent to the circle. All right? Your body on that merry-go-round is always, at every single point, is always going to be moving tangent to the circle. When your friend lets you go, your body is just doing what it naturally wants to do. It wants to keep moving in that straight line motion. And so the reason why you feel thrown out of the circle is simply your body's resistance to change in motion. Your friends were changing your motion by keeping you in, but when they let go, your body wants to keep moving in that direction. Now, this may seem a little unclear, particularly because we don't have merry-go-rounds anymore. But one thing you will, I think, understand is if you've ever been on a roundabout. Okay, so imagine the Happy Valley roundabout, or if you just take a turn really sharp. So in this picture here, you're going to see a car with two drivers, the red and the blue. Notice what happens when they take a turn. All right, you can see the blue driver kind of smushes the red driver. And you've experienced this anytime you've taken a corner turn sharply, or you've gone around a roundabout sharply. You feel thrown to the side of your car, depending on which way you turn. All right, and you might think, oh, that's the centrifugal force. I'm being thrown to the side by this centrifugal force. But that's actually not true. When you're driving in a straight line, your body also wants to drive in a straight line. So you and the car are moving in a straight line. But when the car changes its direction, your body wants to keep moving straight. So watch this. Your body wants to keep moving straight, but when the car starts turning and trying to force you to change your direction, your body wants to keep moving in the straight fashion that it's going. And so that's actually what's happening, is it's your inertia. It's not a centrifugal force. I don't have this slide on the notes, but I want you guys to think about that magic carpet ride that you maybe have ridden on at a theme park, a fair, if you've ever been to Castles and Coasters or anything like that. It's that ride that basically just has you moving in a circle really, really, really fast. And so the fun of that ride is that you always get smushed or thrown to one of the sides. And so think about it. If you were to sit on that ride and you didn't want to get squished, where should you sit? Well, the answer is you should sit closest to the center, because some people would say, oh, the centrifugal force will throw you to the outside of the ride. Well, there's no such thing as a centrifugal force. It's really just your body's inertia wanting to do what it's already doing. All right. Now, let's start going ahead and quantifying all of this stuff. We've talked about a lot of things, so let's actually get some equations here. To calculate centripetal acceleration, I'm going to put a little sub C there so that way we know it's not just regular acceleration, it's centripetal acceleration. To calculate centripetal acceleration, you're going to take your circular speed, which is represented by v, squared divided by the radius. Remember that the velocity has to be in meters per second, and your radius has to be in meters. All right, and then to find your velocity, or your circular speed, remember that it is 2 pi r over t. Now, there is a useful equation here that I'm just going to show you how we get it. Is you can take this value right here, because we know speed stands for 2 pi r over t, and you can substitute that in for v, and if you do that, and if you follow your algebra skills properly, you will end up getting centripetal acceleration can also be calculated by doing 4 pi squared r over the period squared. So both of these equations will calculate centripetal acceleration for you. It just depends on what information is given. If the velocity and radius are given, use the first one. If the radius and the period are given, use the second one. All right, finally, let's revisit Newton's second law. Remember, Newton's second law is force net equals mass times acceleration, and this works the same for linear as well as circular. And so what would that look like for circular? Well, we've already talked about how force net for circles is centripetal force. Mass is going to be mass, whether it's linear or circular. But instead of using linear acceleration, we're going to use centripetal acceleration, which, remember, we just talked about on the previous slide is v squared over r. And so to calculate centripetal force, we can use the equation mv squared over r. All right, we're almost done with this video. We're just going to look at how we can draw some force diagrams. So before we do that, which is on the next slide, let's talk about circular motion does not always have to be a complete circle. An object can be experiencing circular motion if it goes through any part of a circle. So you can see here, especially look at this picture on the right with the roller coaster. The roller coaster has ups and downs and loops and hills and dips. And you can see there that even though the roller coaster doesn't go in a full circle in the picture, when it goes through the dip or when it goes over the hill, it is experiencing circular motion because it is traveling in part of a circle for a little bit of time. With that being said, let's go ahead and practice. What I'd like us to do together is we are going to do two things. The first thing we're going to do is we're going to draw the force diagram for the object going in circular motion. And there's three spots that I want to do that for. The first spot is the roller coaster at the top of a hill. Notice it has the actual circle below there to show you that it is circular motion, but nevertheless he's at the top of a hill. So that's the first one. The second one we're going to do it for is at the top of a loop, so he's upside down. And then the third one is the roller coaster car at the very bottom of the loop. Okay, and then once we draw our force diagram, we are going to write the sum of the forces equation that pertains to the circular motion. This probably is one of the most important things in this unit to make sure you understand and do right. So let's go ahead and do that. So for the driver, or for the roller coaster car at the top of the hill, what forces are acting on the coaster cart? Well, we have the force gravity, that's our field force, that's always going to point down. And then what is touching the coaster cart? The only thing that's touching the coaster cart is the track itself. And so what force would the track exert? Well, it would exert a normal force. And normal force, since the track is below the cart, is going to face up. Now, at this point, some students always say, well, wait, wouldn't friction be a factor in there? You're right, friction would be a factor in there. But if we were to draw friction at the very top of the circle, which direction would it point? It would point directly out to the left, right? Notice that is completely perpendicular to the center of the circle. And vectors that are perpendicular to each other have nothing to do with each other. They are isolated. They are separated from one another. And that's called vector resolution. And so even though there is friction, it doesn't make a difference when it comes to the actual circular motion part. And so even though friction is in reality there, we're not going to draw that because that's really not the most important part of the force diagram. And so our centripetal force, if I'm going to write my equation, is a combination of normal and gravity. Now remember our convention, the force that faces the center of the circle is the positive one. In this case, gravity faces the center, so that's my positive one. And then I'm going to add to it the negative force normal. Force normal is negative because it does not face the center of the circle. All right, let's do position 2. Now in position 2, he is upside down, so gravity still points down. But also, the normal force is still being provided by the track, but now the track is on top. And so the normal force also points down. And so to do our sum of the forces, the centripetal force is going to be still a combination of gravity and normal, but notice they both face the center of the circle, and therefore both of them are positive. So force gravity plus force normal would be my sum of the forces equation. Finally, at the very bottom of the loop, we have force gravity pointing down, and we have force normal pointing up, and this time, force normal is the one facing the center of the circle. And so that's the one that's going to be positive, and gravity is going to be the negative. And before we end this video, I know it's a long video, but before we end, I just want to take a brief moment and kind of talk about how we know in the first and the third example which force has to be greater. In the first diagram there, gravity has to be larger than normal. So the numerical value of gravity has to be bigger than the numerical value of the normal. because when you add those vectors together, your resultant vector has to face down. It has to because it has to face the center of the circle. Otherwise, the object wouldn't be moving in a circle. And so that one, gravity is larger. But if I look at number 3, normal has to be the larger vector than gravity. So normal would have to be a larger value because normal is the one facing the center of the circle. All right, we're going to do some math in the next slide, or excuse me, in the next video. So we'll see you then.